In this video, you'll see a repeat of certain steps from the last video. That's because what I'm going to do here is I'm going to show you how to set up the dual problem and solve it, whereas in the last video we just talked about setting up the dual problem. So I won't spend as much time setting it up since I've already shown you how to do that. But let's take a look at what we're going to start with. We have a problem here, and it's a standard minimization problem because we're minimizing and all the constraints are greater than. And so what we can do is we can write the coefficients of the constraints in a coefficient matrix. So the coefficients of the first constraint would be 1, 3, 15. Coefficients of the second constraint would be 2, 1, 20. And then the objective function, the coefficients are 5, 2 for x1 and x2, and then 1 for the 1c. And then in the last video I showed you how to transpose this matrix. So you transpose the matrix, and then you get the row here would be 1, 2, 5. This row would be 3, 1, 2. And this row would be 15, 20, and 1p. And then from that transpose, you actually get this dual problem. And the dual problem, remember, is a maximization problem where your constraints are less than or equal to, and of course you have to use different variables. So what we're going to do to set up this dual problem, you just look up here and say, okay, we know it's got to be maximized since it's a dual problem, so we make sure it's maximized, and then we have 15y1 plus 20y2 equals p, so that gives us this objective function. And then these are my inequalities. y1 plus 2y2 is less than or equal to 5, and 3y1 plus y2 is less than or equal to 2, and then of course you put your non-negative constraints. Now this is where we stopped in the last video, but actually in order to find the solution to the original minimization problem, we actually have to solve this, and we're actually going to solve this using the simplex method, because since this is a standard maximization problem, we should be able to solve it using the simplex method. There's just a couple of new things you have to do here. So here are the steps for solving a standard minimization problem. You write the coefficient matrix, which we did up there, and then you transpose the matrix, which we did, and we got that matrix there. And then you write the dual problem from the transpose matrix, which we did, and there's our dual. And then you apply the simplex method to the dual. And then finally you interpret the correct solution for the original minimization problem. So now let's take this dual. Let me go ahead and show you how to solve this dual. It shouldn't be too difficult for you because we've already talked about how to solve a standard maximization problem using the simplex method. So we solve this just like we did before using the simplex method. There's just one catch. When you add your slack variables to these two less than constraints, they're actually going to be the decision variables from the original problem. And if you remember, the original problem had x1 and x2. So when we convert this inequality to an equation by adding a slack variable, we use x1 for the slack variable. So that would give us y1 plus 2y2 plus x1 equal 5. And then when we write the second one as an equation, we actually add the x2 to it. And so when we do that, we'll actually get 3y1 plus y2 plus x2 equals 2. And that's really the only thing that changes there. Instead of using s's, we're just going to use the variables from the original problem. And then we do this just like before. We move these variables to the left to get our objective function set equal to 0. So we get minus 15y1 minus 20y2 plus p equals 0. Now, just like before, we put this in a tableau form. Now my variables here are actually, we need a column for y1, a column for y2, a column for x1, a column for x2, and a column for p. Now, unlike before, I'm not going to keep track of my basic and non-basic variables when I solve this problem, because the main reason is I'm not really interested in what the y values are. So I don't really care about what the y values are. What I'm interested in are what are these x values. And it's kind of a clever way. There's a clever way to show you what the x values are once we solve this simplex tableau. But even though I'm not worried about the y values, I'm still going to solve this the same way I did before. I'm going to pivot on the column where the most negative indicator is on the bottom row. So that would be right here. So I'm going to pivot on that column. And then if you divide this number into 5, you get 2.5. And if you divide this number into 2, you get 2. So actually, I've actually got that down here. But the pivot row would be this row right here, because 2 is smaller than 2.5. So I'm going to pivot on this element here. So let's go ahead and drop down here and do that. So here's my pivot element. And so what I want to do to pivot is I want to multiply this row by -2 and add it to row 1 to cancel the 2 to get rid of, just like we did before. So we want to make this a 0, so we just multiply everything here by -2 and add it to row 1. And then 3 times -2 is -6. Add it to 1, we get -5. 1 times -2 is -2, plus 2 is going to give me 0. -2 times 0 plus 1 is going to give me 1. -2 times 1 is -2, plus 0 is going to give me -2. -2 times 0 plus 0 is going to give me 0. And then -2 times 2 is going to be -4, and add that to 5, and I get 1. And then I also want to get rid of this 20, so I'm going to multiply this row by 20 and add it to this row to cancel the -20. Well, 20 times 3 is 60, and 60 plus -15 is 45. 20 times 1 is 20. 20 plus -20 is 0. 20 times 0 plus 0 is 0. 20 times 1 plus 0 is 20. 20 times 0 plus 1 is 1. And then 20 times 2 plus 0 is going to be 40. Now notice I have no negatives on the bottom row now, so I actually have the final tableau. All right, now here's the catch. If you actually solved this like we did before, you might say, okay, y1 is non-basic, so it's 0. y2 is found right here, so it's 2. But remember what I said, I don't really care about y1 and y2. I want to know what x1 and x2 are. Well, if you remember, to get to this problem, we had to transpose, which means we kind of turned the matrix sideways. So if you kind of tilted your head real far to the right and then look at the far right of the x1 and x2 columns, you'll see at the bottom of the x1 column, you'll see a 0. And believe it or not, that's actually the value for x1 in the original problem. And in x2, at the bottom of its column, is 20. And so that's the value for x2 in the original problem. And then, since this problem has the same optimal solution as the original problem, the optimal solution for this problem would be p equal 40. But since the original problem has the same answer, then we can say that c must equal 40 in the original minimization problem. So to make a long story short, to solve this problem, you look at the bottom of the x1 column and the x2 column to get the solution for the original decision variables in the minimization problem. And so the solution would be x1 is 0 and x2 is 20. And so there's your solution for the original problem. And then the minimum value for c would be 40. So the solution would be a minimum value of c of 40 when x1 is 0 and x2 is 20. And so that's how you solve problems by the dual method. So what we're really doing is we're using this dual problem right here and solving this dual problem. But when we solve this dual problem, it's going to give us the maximum value for p, which turns out to also be the minimum value for the variable in our original problem. And then of course to get the x values you just look at the bottom of these two columns to get the x values. So it just turns out that the original problem and its dual are related in that fashion. So that's all I'll do here. I'm going to do another example on the next video. So I'll show you another example of solving a standard minimization problem by using the dual method on the next video.